In this example, we'll practice entropy balance in a closed system. So imagine that we're given a process for which the total entropy of the system is held constant. There are such processes, and we'll be able to evaluate one now. I'm going to represent it as a piston, but of course we don't need to know the details of the piston process or anything like that. It could be any process, as long as the one we're considering has a total entropy that is constant all the time. And we're also going to require it to be attached to two thermal reservoirs. One at TH equals 500 Kelvin, and one at Tc of 300 Kelvin. So once the process starts occurring, we'll have heat exchange going from the hot reservoir to the system and from the system to the cold reservoir. And again, the particulars of whether it's a piston or not are not important. What is important is that the total entropy of the system is constant, and we're also told that as a result of irreversibilities within this process, that it generates entropy through those irreversibilities as a rate of 90 watts per Kelvin. So we're going to need to incorporate that. We're also given the value of Q dot H, which is 30 kilowatts. So 30 kilowatts are being delivered into the system as a result of being attached to the hot reservoir. Okay, so how can we figure out what the power is that is transferred to the cold reservoir? In other words, what is the value of Q dot C? Well, we can use entropy balance. So the general expression is that ds dt equals the sum of all Q dots divided by their associated temperatures plus sigma dot. And you'll remember that sigma dot is the entropy generated by irreversibilities, so that's going to be the 90 watts per Kelvin value. Well, the left-hand side of this, ds dt, that must be 0, right? The total entropy of the system is constant. That means S is not changing. ds dt has to be 0. So the left-hand side is 0. And I just expanded out the sum to include the hot reservoir and the cold reservoir. Now you may see I was very explicit about getting the sign on the transfer to the cold reservoir right. We know that energy should be coming from the hot reservoir, so Q dot H will be positive no matter what, and that's fine. But Q dot C, well, the Q dot associated with energy conservation, of course, will be negative because the system is emitting heat energy into the cold reservoir. I went ahead and put absolute values around Q dot C so there was no ambiguity there, and then put a minus sign out front to guarantee that we get the sense of that heat transfer right. Okay, so we've done that. Now we can rearrange because all we want to do is solve for Q dot C. So the absolute value of Q dot C over Tc equals Q dot H over Th plus sigma dot. And now we can multiply both sides by Tc, which we do to get this expression. So Q dot C, the absolute values around it, is Tc over Th times Q dot H plus Tc times sigma dot. Okay, we'll move all that up. And we know these values. So we'll insert the values for the temperatures. We know both of them, and we should take the ratio in Kelvin. Likewise, Q dot H we were given is 30 kilowatts, and as I said before, that has to be a positive number. 300 Kelvin for Tc, and then sigma dot is 90 watts per Kelvin. I'm going to convert that into kilowatts per Kelvin just so that we can have kilowatts in both cases. All right, so we do that. Q dot C is going to be the sum of 18 kilowatts, which is the leftmost term on the right-hand side, and 27 kilowatts, which is the rightmost term. Sum both of those, and that tells us that the magnitude of Q dot C is 45 kilowatts. So actually what we've figured out is that you have to transfer 45 kilowatts into the cold reservoir in order to maintain a constant system entropy. If you didn't do that, if you had a different value of Q dot C, then your entropy would change. And obviously if you're trying to restrict it so that the entropy of the system is constant, that would be a problem.